This is Team Howard with our final project in ME325 machine design at Iowa State University, taught by Gloria Starnes, PhD in mechanical engineering. Our team members consist of me, Nick Heine, Dain Sires, Reid Schenk, Justin Gross, and Jon Howard. For our project, we designed a gearbox for a plaster saw that would be used by doctors in underdeveloped nations to remove casts. Some of the design constraints are as follows. The motor used will rotate at 10,000 RPM and produce 110 watts. The gearbox must have a 5:1 gear ratio, meaning the cutting wheel will turn at 50,000 RPMs. The gear center distance must be less than 3 inches. The saw must be able to last for at least 100 hours of operation. The material must have a reliability of 99.99% and a bearing reliability of 99.99%. The gears and bearings need to be protected from plaster dust. Because the saw is designed for underdeveloped nations, the gearbox must be cost effective, meaning designed for pre-built gears and bearings. Up next, Dain Sires will discuss our choice for bearings.
Thanks, Nick. The bearings our team has chosen for this project are Dynarol SFR 155s. There are 2 of these bearings required for our powertrain. These bearings will both be positioned on the output shaft of the system. There will be no bearings required for the motor shaft, as there are already internal motor bearings in place. The SFR 155 bearing is flanged and metal shielded. It has a bore diameter of 0.1562 inches and an outside diameter of 0.3125 inches. For the given operational requirements of the assembly, the bearing will be required to cycle 300 million times at a load of 0.3957 pounds. Since the bearing has a dynamic load rating of 81 pounds, we expect the bearing to easily surpass the requirements of the assembly with it. Choosing a bearing that can easily last the lifetime of the device was a big factor of our decision. Another major factor in our project was cost effectiveness. Since the SFR 155 bearing is a common mass-produced bearing, it will be readily available and also inexpensive. Up next, Reid Schenk will discuss shaft design.
This is Reid Schenk, and I will be describing the shaft design of our gearbox. We wanted to make the gearbox as small as possible to minimize both material cost and the bending moments, so the total shaft length in the gearbox is 1/2 inch, including the length of the bearings. The gear is centered between the bearings, creating equal loadings on both bearings. The bearings are located only 0.03725 inches on both sides of the gear at the edges of the housing. The gear will be press fit onto the shaft, and bearings will be press fit into the housing because the forces are small enough to where there shouldn't be any slipping between the shaft and bearings or gears. Since there was only one gear on the shaft, the critical section was obviously right at the gear itself, with the maximum moment at 0.0742 inch-pounds. Knowing that, we calculated the critical diameter using all the K values of a 1020 steel shaft as well as the ultimate tensile strength, and we found the resultant critical diameter to be 0.0674 inches using a factor of safety of 1.4, but based on some gear requirements, we ended up going with a 0.187 inch diameter. From there, we calculated the slope and deflection across the shaft, and both the deflection and slope were extremely small because the forces were so small themselves, and also the length of the shaft is only 1/4 inch, so both deflection and slope were in the 10 to the -6th range, which is well below the specifications for both gears and bearings. The critical speed was then calculated using constant diameter formula, since the shaft is a constant diameter between the bearings. Again, because the length of the shaft is so small, the critical speed was well out of the operating range, and it was at 724,619 revolutions per minute. We decided to go with the 1020 steel because it's a standard, cheap, and reliable shaft material, as well as the modulus values worked out well in all aspects, including deflection, bending, and critical speed. We used Marin factors based on the reliability was set at 99.99%, the surface finish was cold drawn steel, and the cross-section sizing factor also affected fatigue strength. The shaft was designed for 300 million cycles, which is the required application life, and up next, Justin Gross will describe the gears of our gearbox.
My name is Justin Gross, and I will be discussing the gear design techniques. We decided to use high-leaded brass spur gears for this project. They had a 20-degree pressure angle and a diametral pitch of 32 teeth per inch. We assumed that these gears were made by a cast mold, and that they were press-fit onto the shafts. Another assumption was that the pinion gear had 300 million cycles in its lifetime. This is equivalent to a 100-hour lifetime. The driven gear had a half-inch diameter, a 0.187-inch face width, and a 0.187-inch bore diameter. This gear also had 16 teeth. A minimum of 16 teeth was required for no interference with its mating gear. Factor of safety for the driven gear was 2.5 in bending and 1.3 in pitting. Keep in mind when considering these factors of safety that conservative design techniques were used due to poor availability of material properties. The driving gear had a 2.5-inch diameter, a 0.187-inch face width, and a 0.312-inch bore diameter. This gear had 80 teeth. A maximum of 82 teeth was allowed for no interference with its mating gear. Factor of safety for the driving gear was 4.0 in bending and 1.3 in pitting. Next, Jon Howard will speak to you about the housing and hardware design.
Hi, this is Jon Howard, and I will be discussing the housing and hardware design. The housing is made of aluminum and is fastened by 5 machine screws. The specs on the screws are as follows. Grade 5 with 85 kpsi as its minimum proof strength, and the screws are made out of steel. The diameter is 1/4 of an inch. The pitch, 28 threads per inch. And the length, 1 inch, and the grip length of the screw is 1/2 inch. There are no gaskets used for the housing. We decided this because it's extra material and it would make the housing more expensive. Therefore, we really didn't see any problems with not using the gaskets. The smallest clearance is out of a 1/16 inch for any single machine component inside the housing. Some specs for the housing are 2 pieces that are equal in width of 3/4 of an inch, and the machine screws hold the 2 pieces together. The largest diameter is 3.125 inches, and that's the longest cross-sectional length of the housing. The reason for the star design is to conserve material and space, and that is our design characteristics of our housing and hardware. Thank you. This concludes our gearbox design. We hope you enjoyed our presentation.